Imagine that each point in your dataset is like a city. Between some cities are roads, some are short, some are longer, and some don't exist at all. In this metaphor, the roads represent edges, and their length reflects how similar or close to the points are. The closer two cities are, the stronger their connections. And then we represent this strength with a weight. We start by representing our dataset as a graph, where each data point becomes a node. Let's define the terms. Let UV be the set of nodes with n equals to the cardinal of UV, representing the total number of nodes or data points. Let C be a matrix in the space of real matrix of sizes n times d via feature matrix, where each row corresponds to the feature of a data point. And we write C as a vertical stack of row vectors transposed. We first compute the distance between all pair of points, typically using Euclidean distance. We use an exponential similarity function like this. Here, sigma is a parameter that controls sensitivity. Small values mean that only very close points get connected. Large values allow broader connections. In practice, to avoid an overly dense and expensive matrix, we often build a sparse graph. We connect each point only to its k nearest neighbors. It results in a more realistic and computationally efficient network. From this similarity matrix, we construct the graph Laplacian, which compares the entire structure of connections. The classical normalized Laplacian is defined as L equals D minus W, where D is the degree matrix, the sum of weights for each node, and W is the similarity matrix. There are variants like symmetric normalized Laplacian, but we use the basic version here to illustrate the main idea. Next, we apply a spectral decomposition in the Laplacian. This gave us eigenvalues and eigenvectors, which can be thought to as the fundamental modes of variations in the graph. The first eigenvector, with lambda equals to 0, is a constant. The second eigenvector, known as the fielded vector, is key. It offers the best separations into two groups. For more than two clusters, we use the next eigenvectors associated with the smallest eigenvalues. We select the key eigenvectors associated with the key smallest eigenvalues from the matrix U. Each row of U now represents a data point in a new spectral space, where natural groupings are aligned along separate dimensions. It's like rotating the space until the clusters become clearly separated. Visually, it looks as if the data strangles and rearranges into small, distinct clusters. This reorganization happens thanks to the eigenvectors. Now, in this spectral space, the boundaries between groups are clearly more defined. We apply key means to the rows of U and obtain the final clusters, now free from the limitations of the original data shape. Spectral clustering is special because it doesn't rely solely on the shape of the data in the space, but on its internal structures connections. Thanks to the Laplacian spectral decompositions, we can uncover groupings that reflect not just a spatial proximity, but deeper structures of relations and connectivity. And all of this through mathematics that allow us to see data from another dimensions.